In this section, we're going to be looking at chemical analysis. This is part of your chemistry paper 2. The first idea here is to look at what we mean by a pure substance. Now, in chemistry, when we talk about something that's chemically pure, we mean that it does not have anything else mixed in with it. So, for example, it might be an element such as pure gold. This would mean we just have pure, but only gold atoms there. If this were pure water, so a compound, it would contain H2O only. We can help and find if a substance is pure or not by looking at its melting and boiling point. If a substance melts at one distinct temperature, we know that chemically it would be pure. So we can really use this to figure out, do I have something that is pure or do I have something that's a mixture? So for example, here we've got two substances that have been heated and we're recording the temperature over time. Here, what we can see is that as time increases, temperature increases. For a short period of time, the temperature remains constant. Now, this is where the state change is occurring. And as soon as the state change is finished, the temperature continues up again. This change of state is happening at one temperature only. However, over here, what we can see is that actually we've got this gradient that's not quite as steep as before. The state change here is happening over a range of temperatures. So this is indicating that this substance would be a mixture. A substance having a distinct melting or boiling point, so changing state all at one temperature, indicates a pure substance. If we see that melting or boiling point is happening over a range of temperatures, this is our indication that we'd have a mixture instead. The idea about pure substances varies depending on if we're talking about this in chemistry or in everyday language. So in everyday language, when we talk about a pure substance, this means that we haven't added anything to it. It's what we can phrase as unadulterated or in its natural state. So, for example, in life, we might talk about milk. This is not chemically pure, but we refer to it as pure because nothing's been added to it. This leads us on to formulations. Now, a formulation is a mixture, for one mark, that has been designed to be useful, for that second mark. And there's a huge number of products that we use in everyday life that are examples of formulations. With this, the important thing, especially because it's designed to be useful, is that the substances in that formulation need to be made up to specific quantities, and that will give us the properties that we're looking for. There are loads of examples of formulations in everyday life that link to chemistry. So, for example, paints. The different combination of pigments in paints gives them the specific colour that they have. Alloys are also an example of a formulation, as are fuels. Foods also, so we need to follow a specific recipe and have the key ingredients and the correct components. But cleaning surfaces, or cleaning materials I should say, are. And medicines, these are a big example of a formulation. So all the key ingredients are in fixed proportions to give that medicine the properties we're looking for. If you're doing separate science, you study this in a bit more detail towards the end of the topic, but fertilizers are also an example of a formulation. All the different components that a plant needs for growth are added in fixed proportions to that fertilizer. We've got pure substances, but if we do have a mixture, we can use different methods to start to separate this. And this is where chromatography comes in. Chromatography is a method that we can use to separate mixtures of soluble substances and actually help us identify a mystery substance. When we look at chromatography in the lab, it involves two phases. One is the stationary phase. This is the chromatography paper and the piece that does not move during the process. The other section is the mobile phase. Now, this is normally a solvent, or it is a solvent, And typically in a lab you might use water, or if the substance isn't soluble in water, you could use alcohol instead. The idea about chromatography is that the substances that we are going to separate spend some of their time on the stationary phase and some of the time on the mobile phase, and they'll separate out differently according to this. Substances that are really soluble will spend loads of time in the mobile phase, but not a lot of time in the stationary, and so they'll move really high up the paper. While other chemicals that are more insoluble will spend longer on the stationary phase and less time in the mobile phase, so they won't move as high. And the idea about different substances is that actually that time they spend in that mobile and stationary will be different for each of the different substances, and so they'll separate different amounts. So chromatography is a separation technique that we can use to separate different substances that can dissolve in a liquid. We typically do this with food colourings and with inks. The stationary phase in chromatography is the part that's not moving, so this will be the chromatography paper, while the mobile phase is a solvent. And this is the part in chromatography that is able to move. And typically during science experiments you'll use water and maybe alcohol. We need to be prepared to talk around how we set these up, how we interpret results. And for the setup, the first thing that we need to do in a pencil line is we draw the origin along the bottom of the paper. We leave a couple of centimetres between the actual bottom and here, but we'll draw an origin line along the bottom. A common mistake here that happens is that this might be drawn in pen. If this is drawn in pen, the pen is soluble. So actually, during chromatography, your origin line will move. The important thing is that we use pencil as this is insoluble, and during chromatography, it will stay in place. Next, we place the dots of the test sample on the paper. And it's really important here to try and get uniform sized dots. So if you're using like felt tip pens, you would just do a single spot. If you were testing like food colourings, for example, you might drop a cocktail tip into the dye and then give it a dab on your paper. So we need to try and make sure that we've got uniform sized dots that are there and their centre is on the origin line. Next, we'll place the paper in the solvent, and the important thing here is we place it so that the origin line and the samples are above the water level. This means that over time the water will soak up the paper, get to our substance and then transport it hopefully up the paper also. A common mistake to look out for in the setup is that sometimes this line could be submerged underneath the water. If this happens, all of these inks that are soluble will run, but they'll just go straight into the water and they won't go up the paper. When it comes to collecting results, we need to, first of all, leave this some time where actually the solvent front can get up to the top of the paper. Once it's nearing the top, you'll remove this and allow it to dry. And we'll mark in where our solvent front is, so how far the solvent actually got to, and we'll have the origin line already recorded. What we'll then do is once this is dry, we'll measure the distance from the origin up to that solvent front. You can either measure that in millimetres or centimetres. We will then do the same, but for the spot. Now, this is where mistakes come in. You need to measure from the origin line to roughly the centre of the spot. Some people go the bottom, some go the top, and it causes inaccuracies. You aim for the middle. Whatever unit you've measured this value in, do the same over here. So if you measured this in centimetres, also measure this in centimetres. Whichever unit you choose is normally fine, just provided they're both to the same units. Once we've got this, we then calculate the RF value. So this is the ratio of how far the dot moved compared to the solvent. The rule of this is you must always have a value less than 1. So here, for example, if my dot has moved 8.4 centimetres, I'll do 8.4 divided by 12.2, giving me 0.69. If you ever find an RF value that is higher than 1, which isn't possible, it's normally an indication as a common mistake you've divided the numbers the wrong way. Swap them round and it should fix it. But it's the distance moved by the substance divided by the distance moved by the solvent. These RF values are then useful. We can actually use this to identify a substance. So we can look at reference books and find actually the value for that substance in water would have this RF value. Just be aware that if you are finding an RF value for a chemical like a food colouring, its RF value will be different in water than it would be in alcohol. So 2 people could do exactly the same test and get a different RF value. The chances are that one has done it in water and one has done it in alcohol. You could also be asked what the results in the experiment show. Now for here, common things about if it's a mixture or pure. Now A, C and D are all mixtures, and we can tell this because there's more than one spot appeared. A is a mixture, and it's a mixture of 2 pigments. B is a pure substance, and B is also found in A and in D, so the spots match. C is a mixture of 3 pigments. It contains 1 pigment that has no common similarities with any of the others. It has a pigment that it shares in common with A, and it has a 3rd pigment that is in common with D. D is a mixture of 2 pigments, so it contains B and also has a common with A, but it also has a pigment in common with C. If you're ever asked to describe what your results show, just list off everything that you can definitively say about your results. Which is a mixture? How many substances are in that mixture? Do they match with anything else in the different samples? And if you only see 1 spot, it means that it was pure. Or it might mean that the actual RF value of the 2 substances are so similar that you can't tell the difference between them. The other tests that we need to be aware of for chemical analysis are our gas tests. Now we can test for hydrogen, and this is using a burning splint as our test. Our observation will be a squeaky pop. For oxygen, the test is a glowing splint, and when we place this into oxygen, our observation is that it should relight. For carbon dioxide, we will bubble the carbon dioxide or the gas sample through lime water. That will be our test. And our observation is that it should turn cloudy. So if that turns cloudy, it's in presence of CO2. Be aware that lime water is otherwise known as calcium hydroxide. When we test for chlorine, the test is we'll dip in a piece of red litmus, and our observation is the litmus will be bleached and turn white if chlorine is present. If you are studying for combined science, that's now the end of the content that you need for chemical analysis. If you are studying separate science, continue watching for the next section around chemical analysis for separates. So for separates, we also need to be able to describe flame tests, and this is how we identify different metal ions using a Bunsen burner. Now there are different metal ions that you need to be able to identify. Generally the test is that we'll get a sample of our metal on a piece of nichrome wire, and when our Bunsen burner is on the blue flame, we'll put our wire into the flame about 1/3 of the way up, and we'll look for the colour results that we get. Now we need to know our metal ions and their colours. Now lithium will form a crimson red flame. Sodium is yellow. Potassium will be lilac. Calcium is an orangey red flame, while copper will be green. There are limitations or problems with flame tests. Firstly, one colour flame can mask another. So if we've got a mixture of metal ions, it can be really difficult to actually identify which metals we have present. Sodium, that produces a yellow flame, is really a key character there. It's one that can mask the presence of other colours. So the other issue is that if we don't clean that wire properly in between use, we might have contaminant material on there, which again might skew our observation and make it more difficult to perceive the colour. Not only do we need to be able to describe how to test metal ions using flame tests, but also we need to be prepared for how we can test metal ions using sodium hydroxide. So these metal ions are now in solution. So first of all, we'll add a metal ion solution to a test tube, and we'll add sodium hydroxide, and the key word here is in excess. Our job is to observe the colour the precipitate formed, and there are some results that you need to be prepared for. Once we know the colour, we should be able to identify the metal ion from there. Now, these are our metal ions that we need to be aware of. First of all, to help keep this straight, because there are 6, 3 of them are metals that are found either in group 2 or group 3. And notice they all form white precipitates. So any metal in a group, doesn't matter if it's 1, 2 or 3, will all form a white precipitate. The only one that's slightly different is aluminium. This will still form a white precipitate, but if we add sodium hydroxide in excess, eventually this will dissolve. That one's unique for aluminium. The rest in group 1 and 2 actually will all make white precipitates. The only ones you're expected to know is calcium and magnesium in group 2. However, when we get to the transition metals, these are now more colourful. Now with these, you just need to know copper, which makes a blue precipitate. So it's a green flame, but a blue precipitate. Iron 2 is green, and iron 3, so that's a reference to a 3+ ion now, is brown. So we need to know these metals and their precipitates also. There are problems also with this test. And the issue is here. When we add sodium hydroxide, if you get a white precipitate, provided you continue to add it in excess, you'll know that you've got aluminium. But if you continue to add and the white precipitate still remains, you won't know if you've got calcium, you won't know if you've got magnesium. You will not be able to distinguish which one's which, because they're all making that white precipitate. So, as I've said, if we continue to add the sodium hydroxide, eventually the aluminium will disappear. So we can start to identify, right, that might be aluminium. But if the precipitate doesn't disappear, you'll have no way of knowing was that calcium or magnesium. So that's a definite limitation to that method. As well as having to identify how to test for metal ions, we also need to be able to describe for negative ions too. Carbonates is quite nice and straightforward. First of all, we're going to add an acid to the solution. If carbonates are present, we'll make carbon dioxide gas. And so we'll bubble that gas through lime water, and if it turns cloudy, carbon dioxide was made. That indicates it was a carbonate. So if we add a carbonate to acid and lime water turns cloudy as a result, that's a positive result for carbonates. Halides are slightly different. Now the important thing here is we are going to add a nitric acid. So we're still acidifying the solution. We will then add silver nitrate to the solution also. So we're adding 2 chemicals. The way of remembering these, because you will need to remember them both, we've got nitric acid and silver nitrate. So we've actually got the same negative ion being added twice. We're adding loads of nitrate ions. So nitric acid and silver nitrate. And we look for the colour that this will turn. With our halides, they get darker as we go down. chlorides will be white, bromides will be cream, and iodides will be yellow. A common question is you might get asked why it would not be appropriate, as I go back, to add hydrochloric acid instead to the solution. If we want to identify a halide, we're identifying a group 7 element, or ion from group 7. If we were to add a hydrochloric acid, we would definitely get a positive result because we'd be adding halides to the solution. So we cannot use hydrochloric acid because you would 100% get a positive result for chloride ions. You've added them in. So this has to be nitric acid that we use, and we'll combine that with silver nitrate. With our sulfates, it's the same problem. We cannot add sulfuric acid to the solution because we'll add sulfate ions. We'll get a positive result. So now we use hydrochloric acid. So we've acidified this, and we now add barium chloride. So the chemicals you're going to have to learn, but hydrochloric acid pairs with barium chloride. So we're adding these chloride ions twice. If a white precipitate is made, then sulfates are present. So as a summary for our tests, in each of these we're going to acidify. So with a carbonate, we add a dilute acid. It doesn't actually matter which one, and we'll bubble that through lime water. And our positive result is it will turn cloudy. For sulfates, we also need to acidify. We now can't use sulfuric acid, so we'll use hydrochloric acid and pair that with barium chloride. If sulfates are present, this will also turn white. And the precipitate is a reference to a solid. To test for our halides, we'll now use nitric acid and we'll pair that with silver nitrate. So those are our two chemicals. For our positive result, the chloride will have a white precipitate, bromide will be cream, while iodide will be yellow. So they get darker as we go down that group. This does mean that you need to be prepared for a possible 6 marker about how we could determine the ions present in a mystery solution. So first of all, we kind of need to take some multiple samples from this. So we could take a sample, add sodium hydroxide, or we could do a flame test. You could do both. You would then have to take 3 samples to test for your negative ions, to test for your carbonates, your chlorides, your sulfates. So you do a separate test for each. When writing your method, you would go through, right, this is how I'll test for sodium hydroxide, this is what my results would be, and then you repeat for your carbonates, your halides, and your sulfates. That leads us on to instrumental analysis. Now this is a way of using equipment to very quickly and precisely detect elements and compounds. And it is very precise. We can detect very small quantities of these. The huge benefits of using instrumental analysis is that it is incredibly accurate, very sensitive, so very small concentrations of these substances can produce a positive result. And it's rapid. Flame emission spectroscopy is an example of chemical instrumental analysis. And this is one in which we can use to analyse metal ions in solutions. A sample is put into a flame and the light given off is passed through a piece of equipment called spectroscopes. And you'll get this output known as a line spectrum. And what we can do is match up the lines on the line spectrum to different samples to identify the substance or the metals that we may have present.